So we're looking at section 1.2, and we're going to start our analysis of graphs on the front of worksheet 3. And then on the back, we're going to discuss symmetry. So the beginning of this lesson should feel reviewy. We're going to discuss domain and range again, but we're going to really hit hard the difference between X-intercepts and Y-intercepts, which I know sounds really common and basic, but they're also very easy to mess up. So when you're looking at a function, you can determine the domain and range and estimate all these things. But you're going to have to use some other techniques if you want to get exact answers, which is we're going to talk about the difference between those two things today. Estimation's great when it's called for that, but sometimes I just want the actual answer. So big difference here, guys, between an X-intercept and a Y-intercept. So the X-intercept of a graph, also known as the zeros of the function, is when you take your function, whatever it is, and you set it equal to 0 and you solve it. So for the last few weeks, it's been a lot of quadratics that you guys have been solving through various methods. When you're finding the solutions to your quadratic, you're finding the X-intercepts or the zeros. But there's another concept out there known as the Y-intercept. And we know the Y-intercept is where your function crosses the y-axis. But if you think about what that means for the ordered pairs, it's when you plug in, the fancy word is evaluate, but when you plug in x equals 0, that's how you're verifying that you have what's called a Y-intercept. A Y-intercept means different things for every type of function, so you just have to know how to find it. So, I know you guys are like, why is she talking to me about this? We've done this for years. Like, yeah, but sometimes they get confused. So ignore the set builder notation on this set of notes. This is from your textbook, so they gave you both. Are we okay with saying that this quadratic has a domain that stretches from negative infinity to infinity because it goes forever left and right? Okay, we're all good with that one. Now, as far as the range goes, I think we can all confirm that the range starts at negative infinity. But the maximum of that parabola is going to tell you where your range ends. But someone remind me, if I'm looking for range, do I look at the x value or the y value of the maximum to determine? Yeah, it's the y value is the end of the range. Very good. So they ended it at that number, which they had to find either through algebraic methods or I'm sure in their case they just used the calculator. Okay? Let's talk about the Y-intercept. The Y-intercept, which I kind of drew too big, but this little blue thing I'm trying to draw on, estimation-wise, I can see it kind of sort of crosses in between 4 and 5. I can't really tell anymore where it crosses because it's scribbled all over it. But if you're going to find the Y-intercept algebraically, which is the best route, that means you're going to plug in x equals 0. So they did that for you. And apparently it's 4.5. Which is kind of where I estimated it. So good job, me. Now finding the X-intercepts. Again, we can estimate them because it's where they cross the the x-axis, excuse me. But we all know that algebra is a little trickier than that. It's usually not where you think it is. So they said you should set it equal to 0. So set your function equal to 0 and solve. So they chose factoring. I'm going to be honest, guys. I don't think I would have factored with the decimals, but whatever. I probably would have done another method. But to each their own. And they found your two solutions and your two X-intercepts, your two zeros, to be at negative 3 and 1.5. And maybe that's exactly where you estimated them, but I think we're all savvy enough about algebra, like, you can't just assume the graph is right. So if I give you a function as well as a graph, you have to get the actual answers. You can't just estimate them unless you're clearly the directions say, please estimate. So let's practice this one. I want domain and range, which should be pretty easy. And then I want you to approximate the Y-intercept, but then we're going to come back and actually find it. And then we're going to approximate the 0, and then we're going to come back and find it. We're going to do this in pairs, which I'm going to start off with my favorite pair. You don't have a pair. We'll make you a pair. Domain! Talk to me about domain. How far left and right is this guy going to stretch? Yeah, Thunder Stealer back there. I heard you. Alright. And since you don't have a pair right now, can you give me range too? Yeah. That one wasn't too bad. Now, it wasn't a polynomial. It was, if I look at the actual function over here, it's a cubed root function, which notice, yes, on Friday, we did a lot of work with square roots and even roots as having domain interruptions. This is not an even root. This is an odd root. Odd roots don't have any interruptions. They go forever. So just like a polynomial has infinite domain and range, so does a cube root and a fifth root and this whatever, anything odd. All right, let's talk about Y-intercepts first. So, add up. Can you help me estimate the Y-intercept? And you're just basing it off of the graph. Now be careful, they're counting by twos. They get me every time because I don't realize they're counting by twos. Yeah, so we're thinking that the Y-intercept, and I'll write it as an ordered pair, we're thinking it's 0, -8, and now neighbor's going to help me confirm that it's at -8, and the algebraic way that we confirm a Y-intercept is you plug in 0 for your function. So your function over here, if you plug in x equals 0, let's see if he's right. All right. Right here, kiddo. Cube root of -1. This is what everyone panics. They're like, wait, what? And you can definitely type it. Cube roots are just like something multiplied 3 times that gives you a -1. What would that thing be? It's not +1 because that'd be +1. It must be -1, yes. So cube roots can be negative because negative times negative times negative is negative. So this thing I just boxed in is -1. So this is really like 4 times -1 minus 4. So are we able to confirm that his -8 was absolutely correct? Awesome. All right, so that's what an algebraic confirmation would look like. Check, check. We're going to see an example coming up where the graph appears to be one thing and then turns out it's totally not right. So let's do similar here for the zeros, which are your X-intercepts. There's only one of them. Riley, can you tell me approximately where you think that is? The X-intercept, where do you think it is? Flip that around, 2, 0, and I'm with you. Yeah. So this time it's an x-axis intersection, so 2, 0. And then we're going to confirm it by going to our algebra. And this time, instead of plugging in 0 for x, you want your function to come out to 0. So, Taylor, you're going to help me solve this. Now, technically, I could just plug in Riley's guess. It's not really a guess. It's totally right. But we should probably learn to solve it without guessing. All right, Taylor, help me solve this. Your first step would be to move this 4 over by adding it, yep. So, what do we have here? We have 4 equals 4 times the cube root of x minus 1. So next thing is to move this 4, divide it. So we have 1 equals the cube root of x minus 1. Now you have to undo a cube root. So when it's a square root, we square it. So if it's a cube root, we cube it. And this is a little boring because 1 to the 3rd power is still a 1. So 1 equals, now it's x minus 1. Bring it on home, kiddo. X totally equals 2. You were right. Check. So we're estimating from the graph, and then we're having algebraic techniques to confirm it. If this was a test question, I wouldn't make you do both. I would either have you do one or the other, and I wouldn't be sneaky. Whoops, I don't know what I just did. I wouldn't be sneaky and probably put some, well, no, I wouldn't be sneaky on a test. I might be sneaky on your homework. All right, let's take a look at this question. Nice absolute value function. So here's the function. We also have a graph, and we're going to do something similar. There is a test question just like this. But on the test, I don't give you the function itself. I only give you the graph. So you have to like base your answers off of the graph. Unfortunately, this is a pretty bad question for some kids because they have a major concept mistake. So when I look at this question right here, this very first one, Daniel, I'm going to talk to you about this one. What are they asking you to do when it says f of -2.5? Yes, so that's an x value, and they want you to either graphically or, in another case, your partner is going to do something else. So you're going to do it graphically. They want to figure out what happens when x equals -2.5. So he's going to go over to x equals -2.5, which is roughly right here, and then find the function's output. What do you estimate it to be? Yeah, good estimate. And if that's the way it is on your test, there's not going to be an actual algebra expression anywhere, so you're going to have to just base it off of your graph, and I would accept that. If you think it's like 12.2 and I think it's 12, I'll just call it good enough. They're going to be estimations, so I have to give you a little leeway. But because we have a function, we can check it. So we're going to check Daniel's work. Yep. We're going to check this one, okay? We're going to plug in a 2.5 into your function. So 2 times the absolute value of negative 2.5, thank you, plus 3, and then plus 1. So absolute value evaluation, you're supposed to start on the inside of the absolute value bars. Negative 2.5 plus 3 is just 0.5. And then what happens when you take the absolute value of something that's already positive? Hey, Thunderstealer. It's just going to stay positive because it's measuring distance. Did I do something wrong, though? It's a minus 3. Oh, ignore me. Oh, man. I'm just setting you up for failure. Okay, so that is not 0.5. That's 5.5, and it's negative 5.5. So now tell me what happens when I take the absolute value of negative 5.5. Now it's positive 5.5. Yeah, it's because it's measuring distance. So 2 times 5.5 plus 1. Daniel, you were right. She confirmed it. Check. All right, what about 1? Miss Jasmine, what do they want you to do with f of 1? Walk me through this. Yeah, somehow I got to figure out what happens when x equals 1. So I'd like you to do this one by the graph. So x equals 1, follow it up. What do you think the output is? I'm thinking it's 5. And we won't know till we confirm it. All right, Taylor, let's confirm. To absolute value of, let's see if I can do it right this time. 1 minus 3 plus 1. Start on the inside. Yep, absolute value of that. So you got 2 times 2 plus 1. Plus 1 is 5. Check. All right, good job. So this is usually in the lesson where your teacher's like, I'm bored, let's move on. But we can't, because this one's going to be weird. And because it's going to be weird, I'm going to give it over to Sky. She's like, why? All right, Sky. X equals 7. Yeah, that makes sense. Totally looks like 8. You've convinced me. But not Hallie. It's like, no, we're going to check it. All right, 2, absolute value of 7 minus 3. Let's see if I get it right here. Plus 1. All right, start on the absolute value bars. 7 minus 3. Absolute value of 4. 2 times 4 plus 1 is 9. Who's right? Yeah. The answer's 9. The algebra does not lie. The graph totally does. So the graph, I'm with you, Sky. It totally looked like 8. And if it was just simply an estimation question and I didn't give you a function and you said 8, I would have been like, yeah, you convinced me. But because we had a function and we know that functions supersede graph interpretation, the output's actually 9. The graph is just, a lot of things could have happened there, guys. Could have been a photocopy skew. It could have been like I pulled it from a file and I stretched the file and it doesn't look right anymore. It could just be some jerk, not me, was trying to make you misinterpret it by giving you a false graph. I mean, I wouldn't do that. Yes, ma'am. Yeah, and I'll be honest, I don't think we do this to you on a test because that seems really mean. But just know that the function, the algebra, supersedes the graph. The graph is a good estimation. The function is actually the answer. All right, that was fun. Oh, domain and range. Why not? Now I am a little bored, so I'm going to move on to number 4. Aiden, can you tell me the domain for number 4? Remembering domain stretches from left to right for your x values. Yeah, and what kind of symbol do I have on the 4? Nice. Notice he ended the domain with a bracket because there is an x value at 4. But infinities always have parentheses. Brandon, can you help me with range? Very nice. What kind of symbol on the 3? Bracket. Very good. So there's the reason why you'd look for an open parenthesis, like a softer parenthesis, is if you had an infinity or if you had an open circle. Thank you. Or if you had an asymptote, which we're going to see on the next example, where they like scoot on forever and don't actually get there. Piper, it's you. You lucky ducky, you. All right. Thank you. And just for that, you're going to help me with domain of this one. Okay. This is a weird one, though. All right, so domain from left to right. So it's trucking along, do, and then something weird happens. Now, first of all, can you tell where something weird happens at 0? Yes, there's what's called a vertical asymptote right here at x equals 0. So, if your domain starts off fine and then has an interruption at 0, do you remember how we wrote this as an interval? Yes. Good? So, if you put a bracket, you're telling me there's something good at 0 that actually exists, and we don't have that. So let's close it with a parenthesis. And then you got to hop over to the other side of 0. Yep. Yep. Very nice. Enrique, be inspired by Piper. I want range. Starting with, how low did this go? Yeah. And then the curve, if you follow it from low to high, like it's trucking along, and then something weird happens here, and then it picks up here, and it keeps going up like this. So first of all, can you figure out where this location of the asymptote is? I know it's a bit of an estimate, but where do you think it is? It's at 0. So I think you're pretty much the same thing as Piper then, aren't you? Negative infinity, the y's get interrupted at 0. What kind of a symbol do I put on 0? I don't hit 0 because of the asymptote, so I have to use a parenthesis. And then you got to jump over 0 to get to the other side of it. So again, you start with a parenthesis. And then it goes up until infinity. All right, so that was weird. Their domain and range looked identical. That only was because you had a special rational function that had both a vertical and a horizontal asymptote at 0. We're going to have a whole unit on rationals later where they don't always have that. Yes, Dean? That's a bit of an estimation. Yeah. Well, if that was to occur, there would be something in between 1 and negative 1 also. Like there'd be like a weird parabola looking thing. You don't know that yet because we haven't done that unit. Okay. So if this was on a test question, you could either ask for a little help on the interpretation, or I would be a little liberal with my grading. Okay. Oh, we're on the back now. Time for symmetry talk. Okay, so today we're going to be looking at functions in graphed form, but also in algebraic form. And I'm going to ask you about symmetry. And then I'm also going to ask you about even and oddness, which those concepts kind of go together. Now, don't confuse even and odd today with even and odd degrees. Like a lot of kids, anytime they look at the exponents, they're like, oh, it's got an even exponent, so it's even. That's not what we're saying today. Okay, that's not 100% true. So, first of all, let's talk about, this is out of your book, this is just a graphical representation of symmetry. If you were to fold your graph along the x-axis and it maps onto itself, that's called x-axis symmetry. And your book gets really fancy and it says it's symmetric about the x-axis or symmetric with respect to the x-axis. If you just call it x-axis symmetry, I'm good with that. But think about the ordered pairs here, guys. I'm just going to make up an ordered pair. If this was the ordered pair 2, 4, what do you suppose this symmetric point down here would be? 2, -4. And that's really easy for you guys to see as a graph. It's a little harder to interpret when it's algebra. I'm going to be honest, we don't really do a lot with x-axis symmetry because it doesn't have a test that we're going to talk about. But we're going to talk a lot about what's called y-axis symmetry. So, symmetry to the y-axis, or symmetric with respect to the y-axis, is just what you think it is. Whoops. If you fold it along the y-axis, you have some point symmetry where, like if this was the ordered pair 1, 3, what do you suppose this symmetrical point over here is? -1, 3. Very good. So while the x is opposite, the y hasn't changed. So, I'm going to tell you this on the next screen in a moment, but y-axis symmetry, these functions are known as even functions. We're going to write that down in your chart in a moment. And then there's something called being symmetric with respect to the origin, or origin symmetry. So the origin symmetry, the point representation kind of makes sense. So like if this was the ordered pair, again, I'm just making this up, 1, 3. This ordered pair down here would be -1, -3. So it produces an opposite x and an opposite y. If If you want to look at the visualization of it, to use a little kid term, what if you took your paper and you folded it hot dog and hamburger style? You remember those? Yeah, that's what symmetry of the origin is to me. So like this way and then this way, it would map onto itself. Okay, that's what symmetry of the origin looks like. What some people interpret it as is what's going on in quadrants 1 and 3 is the same as what's going on in quadrants 2 and 4. You know, they're the same. That's symmetry of the origin as well. Symmetry of the origin is a little harder for kids to spot. So we're going to be doing algebraic testing today. By the way, symmetry of the origin, these functions are referred to as odd functions. All right. This is the chart that's on your notes. So the first thing I have a problem with is they refer to what's called x-axis symmetry, which I'm not going to get very creative today. I'm just going to draw like basically the same one we just saw. So a sideways parabola, like so. And then it describes the ordered pair changes of what happens where the y value is going to be opposite. We don't really do any algebraic testing for this, so I wouldn't worry about that. And then this is what bothers me. It says, what kind of function is this? Well, I have a really big problem calling this a function. It's not a function. So the first thing you might want to write down is these are not functions. But if you're looking for an algebraic statement that would represent one of these, that would be like x equals y squared. We saw that on like 2 lessons ago where if you tried to solve for y, you'd have both positive and negative square root of x. So you were getting 2 different outputs. That's why it wasn't a function. Don't really get hung up on x-axis symmetry, guys. That's just one of those, like, if you see it, you see it. You don't have to test for it. But y-axis symmetry, this is a big one for us. Okay, so first of all, give yourself a drawing of something that has y-axis symmetry. So since I apparently have no creativity today, I'm going to draw a parabola. Good old parabola. It starts with origin. Why not? I want you to write a big note to yourself that y-axis symmetry, these functions are known as even. And then the algebraic test is written a little weirdly. What I want you to write down is that if you plug in a negative x into your function, you just get back the original function again. Okay. I know that notation is a little weird. You'll see it in action in a moment. Yes, Dave?
So is it only like y-axis symmetry if it is started at the origin?
That's a good question. Could you transform this parabola and still have symmetry of the y-axis?
I think so.
How would it be okay? Because yes and no. If I moved it to the right,
it's symmetrical, but it would be at like x equals 2.
so that wouldn't be x. That wouldn't be the axis symmetry. So what if you moved it up or down? That would be okay.
Yeah.
And that was going to be my next point.
Okay.
So y equals x. You're like a good prophesizer. So y equals x squared, totally good. Y equals x squared minus 4, totally good. The thing we can't do, though, is shift it to the right and to the left, which we can see an algebraic example of that in a moment. All right. And then origin symmetry. I'm not very creative today, so I'm going to draw a very boring cubic function. These functions are known as odd. The algebraic test, what happens is if you take your function and you plug in negative x, you're going to get out negative f of x, which is just a very fancy way of saying opposite. So whatever your original function was, you're going to get out the exact opposite function to it if it's odd. So some examples of opposite, or I should say odd functions that have symmetry of the origin would be like y equals x to the third. Now this one you have to be really careful about shifting it, because if you shift it up or down, you no longer have that symmetry that you needed. You can stretch it. Here's my favorite. Sine of x. Oh, who remembers sine? Oh, none of you? That's okay. So sine we're going to revisit in the winter, like February. Unless you're in trig, then you're going to see it like now. Like now. Yeah. Are you doing them now? Graphing? Oh, have fun. Alright, let's see this in action, guys. So this one's kind of already done for you. Mrs. Hoffbauer likes when you guys kind of take a peek at the graph. So she gave you a peek at the graph there. So based on just the graphical representation of it, do you guys see any sort of symmetry on that graph? Do you suppose it's Is it x-axis, y-axis, or origin, if anything? It appears to be origin symmetry, yeah. And the only way that I would be able to confirm that is through the algebraic test. So in order to test it for being an odd function, is you take your function and you plug in a negative x. And if you get the opposite function back out again, that means you have an odd function, or a function with symmetry of the origin. So they kind of already did this for you. They took your function, which is this guy, and they plugged in negative x's for all the inputs. So now your job is to simplify this. This is kind of where the problem occurs. Guys, think about order of operations. You got to do your exponents first. So you have negative x raised to the third power. What happens to your negative sign when you raise it to the third power? Stays negative. So this guy right here, there's like a negative coefficient, and then there's a negative x to the third power. So what happens to that term? This becomes positive, yes. So it's positive x to the third plus 2x. Notice I changed the 2 times negative x. No, Abruzzo, you didn't even do that right. Try again. Notice how I totally changed it to a minus. Okay, there we go. So x to the third minus 2x. So you plugged in negative x, you cleaned it up a little bit, and now I want you to compare this to the original. Well, they're clearly not the same. Are they opposites? Opposite meaning they look the same terms, but everybody has the opposite sign from the original, and that's a yes. So since these have opposite signs, that means we are indeed an odd function. And you're going to write with symmetry, I think there's blanks here for you guys to do it. I just wrote over my blanks. With symmetry of the origin. If you want to get fancy and say symmetrical with respect to the origin, that's fine. That was weird. Okay, let's do the next couple without looking at the graph. Okay, let's pretend we don't have a graphing calculator and I need to know whether these are even, odd, or neither. So it doesn't matter whether you think it's even or odd because the test starts out the same way. The test starts out with you plugging in a negative x into your function. So I'm going to go to my function and I'm going to take out all the x's, and instead of an x I'm going to plug in a negative x. But now I need your help simplifying this. So this term right here, the negative x to the third power is going to create what sign? This is a negative x to the third power. So when you combine that with your 4 coefficient, you have negative 4x to the third power. And then I'm just going to drag down the plus 1. All right, y'all. Please compare 4x to the third power, negative 4x to the third power plus 1, to the original. Are they the same? Are they opposites? No. Why are they not opposites? Yes, this plus 1 never changed signs. So because that's not an opposite sign as well, it's not the same, it's not opposite, so it must be neither. That's all I need you to say for me, guys, neither. Don't worry about x-axis symmetry. Just concentrate on even and odd for this. All right, so number 7, same thing. It doesn't matter whether you think it's even or odd because you're going to test it the same way. So take out all your x's. Whew, hello. And then in place of them, put a negative x. And then we just got to clean it up. So right here, what's going to happen to the signage of that first term if it's negative x raised to the 4th power? It's going to become positive x to the 4th power. Good. All right, and then right here, same thing happens. Even powers create positives. So that's positive x squared, but there is a negative 10 coefficient, so it's back to negative 10x squared. And then plus 9 isn't going to change at all. So could y'all compare this new one to the original? And what do you know? They're the exact same. So since they are the exact same, what does that tell you? Yes, that's the test for even. So they are even, which means you have symmetry of, look back at your chart, which one's even? Y-axis, very good. if you had graphed that, you would have seen the symmetry of the y-axis. But we just learned earlier today that sometimes graphs are misleading. So keep that in mind. Oh boy, number 8. Look at that. Let's go ahead and plug in a negative x. And then simplify it, of course. So what's going to happen to this denominator's term if you raise negative x to an even power like that? You're just going to come back to a positive, right? So 5 over x to the 4th back again. So if you would please compare that to the original. They're exactly the same, which means it is even. Very good. So bring it on home. Since this is an even function, that means it has symmetry of the y-axis. Very good. All right, one more here for algebra. We're going to test it by plugging in negative x. All right, watch your signs, though. This first one, negative x to the 3rd power, is going to create a negative x to the 3rd. And then negative 6 times negative x will create a positive 6x. And when you compare the original to this new guy, what do you notice? They are opposites, which means they are, this is, I should say, odd. Yes, very good. So we notice they are opposites, which means this is an odd function, which means it has symmetry with respect to, no, origin. So this is where it gets a little confusing, because you're like, wait, what? So we actually don't have a test that we've been using for the x-axis symmetry, so maybe just don't think about it. You're only testing for even and odd, and the only way I can remember that odd and origin and opposites go together is because they all start with O, so that works out well. Opposites, odd, origin. Opposites, odd, origin. Okay. Good deal. This time I give you both. I give you the graphical representation and I give you the algebra representation. So let's use the graph since it's staring at you to make an assumption, and then we'll test it out to see if we're right. So based on the graph, do you guys feel like this is x-axis, y-axis, or origin? I'm thinking origin, yeah. If it's twinsies in opposite quadrants, then you might have origin symmetry, okay? Remember, that's the folded hot dog, folded hamburger. Okay, so the test for origin symmetry is where you plug in a negative x into your function. So here's your function. Instead of over x, we'll call it over negative x. Y'all simplify that for me. That becomes a positive 2 over x. So can you please compare that to the original? Well, they're clearly not the same, so good call on not calling it even. Are they opposites? I think they are. I know why you guys are saying no, because you feel like there should be 2 negative signs. Guys, 2 over x is one term. Because if you had 2 negatives, it would be positive. Those are opposites, yes. They threw a negative in front of the function is what happens. So, indeed, this is an odd function, and it has symmetry of origin. Now, to be truly misleading, we put the wrong function on this one. I don't know why. This is not even the graph. Guys, look at the function. Negative coefficient with x to the 5th power. That does not look like a parabola. 5th power is like one of these weird squiggly doohickeys. It does like this. Okay, so I'm sorry. I don't know what happened. That was very misleading. I guess you can't trust anything your teacher tells you anymore. I wouldn't do that to you on a test, okay? That was just, I think, a typo. So let's go ahead and test. Does anybody have a feeling for what it is based on the algebra?
Yeah, x-axis.
You feel like it's x-axis? Well, we don't have a test for that. Origin? Maybe. Let's test it.
No, it's not origin.
Well, you never know until you try the test. And that's actually going to be part of your question, right? So we have negative 0.5, whatever, to the 5th power minus 3. All right, now if we're plugging in a negative x here, the negative x to the 5th power, this will create a negative x to the 5th power. But then you have a negative 0.5 coefficient in front of it. So this is now a positive 0.5 x to the 5th power. And then minus 3 doesn't change. So carefully compare this to the original. Well, they're not the same.
Neither.
This one's neither. Ultra tricky. My bad. Whew. So I know what you guys are thinking. You're like, well, how do I know if it's x-axis symmetry? You would be looking at the graph and it would fold like this. Okay. The internet can't see what I'm doing, but I'm totally folding hamburger style. Okay. I'm trying to peek at your homework here. I don't even think we ask you about x-axis symmetry on the homework, and it's definitely not on your test, so don't worry about it. So your job for the homework is to finish it because it's your last thing in your homework check, okay? By the way, speaking of homework checks, I don't even know what happened, guys. Something happened with our... Let me find it. Not there. Alright, well, something happened with our homework checks where, like, half of your homework checks got numbered weird. So, just so we're all crystal clear... The lucky duckies who have homework checks who look like this have the right numbering. So, like, the people who have it wrong, it's not your fault. It's our fault. It started auto-numbering down here. This is not section 1.3 and 1.4. So check your homework page and make sure that you scribble out those. If you have the wrong ones, half of you have them right, half of you have them wrong. They should look like this. The book assignment today is called 1.2.
Dang it, I have.
Oh, you have the wrong one. Oh, no. There's no way to fix this. Fix it. Okay. So this is the last item in your homework check. You have gobs of time right now to get going. I'm going to stop the video, but I'll pull up I put the PDF, or actually Hofbauer put the PDF of the bookwork up for you again. So we'll pull that up. Good luck.